Prairie, are you there?
Yeah,
We here.
Okay. You still, the picture on your that I'm seeing is real blurry. What about y'all?
We can see you fine.
Okay, well that's all that's really important. Okay. Picking up, I sent out a couple of spreadsheets to play with, and I'll show you a little bit of them. But they're designed for you to be able to play around and to look at different barriers with different heights and different widths. When we left last time, we had set up and worked through basically the coefficients of the barrier. I want to talk a little bit about transmission coefficients and where they come from. I don't plan to necessarily probably go through all of it because I wrote it up for you to read, and I can tell you, but unless you put pen to paper and do the thinking for yourself, you're not going to ever really understand them. In the original case, where the energy was greater than the barrier, I make the following statement in your notes that the probability of reflection, called the reflection coefficient, is the ratio of this V over A. And I actually solved just before that that ratio had to do with the differences in the wave number. So this is the wave number in the second region, and this was the wave number in the first region, divided by the sum. So obviously if the material, let's say there was no barrier. If there was no barrier, then the region before the barrier would have wave number K1, and the region after the barrier, since there is no barrier, would still be K1. And you'd have K1 minus K1 is 0, and you get no reflection, you just go transmit it through. So if there's no barrier, you have 100% transmission. If K2 gets bigger, then it looks like your reflection coefficient goes up. And that's kind of what you would expect, okay? So I made kind of a simple step barrier to do that sort of thing. And let me show you that. So I gave you a little software, and inside of this I actually have computed out not just the K1s, but using the formula that's on Iceberg and Resnick's page, which is, a second, let me go back, this page right here in Iceberg and Resnick's book. He goes through the examples like I have, and he calculates if you're below the barrier, your energy is less than V naught, what the formula is, and then he does the case where it's above. So here the energy is 1.5 times the barrier. Here it's 2 times the barrier, so the particles should go over. Even though it goes over, you can see that when you get over the barrier, you don't instantly go to 100% transmission. This is seen if you send an electromagnetic wave down. If you send the wave down and you don't have a matching on the end in terms of the impedance, some of the energy that you send to a household gets reflected back to the power company. You'll be glad to know the power company charges you whether you reflect it back or not. All right? If you have a lot of motors, like for instance in a company at FMC, they have a lot of inductance because they have windings. You can be reflecting back 70, 80, 90% of the power back to the power company. So that means you're only getting 10% of what you pay for, so your electric bill is 10 times what it needs to be. So on the wall, they'll have big capacitor banks that you change the capacitance and cancel that out so that you get those impedance matched. Same thing happens here in quantum. These things are different impedance matching that actually will get it bounced back, and you don't get 100% transmission. Some of it, like right here, that percentage would still get reflected. So what I've done is I've taken, and I've actually built you a spreadsheet of this. And you can play around inside with the height of the barrier and so forth and see what it does. So one of the things I sent you is this spreadsheet. And you can go in here if you want, and you can change out how much you add or change away from the barrier and see when you start getting transmission. So for instance, if you're 30% above the barrier, 12% is still reflected. If you, on the other hand, were somewhere further down, say at 40% above the barrier, you still have 9% reflection. All right? So you can go in here and play around with this. It goes to 254%, and there's still 1.5% reflection. All right? This number and this number have to add up to 100%. That's the probability of reflection, that's the probability of transmission. Now I did that partly not because this one's that exciting. This is kind of a boring one. You have a single step. It's an infinitely long step. And so if you're below the barrier, you never get any transmission. If you're above the barrier, you get a lot of transmission. Whoopee. The main reason I did it is because I wanted to study these transmission reflection coefficients for a barrier that's not infinitely long. Because that's what you really want to build in a semiconductor or what have you. So what I really want to do is I wanted to do the problem where you have this barrier, some width and some height. And I wanted to find out how sensitive and what would happen if you were below the barrier, but also what happens if you go above the barrier? Do you get 100% transmission? Or do you only get 40% transmission? Classically, you might think, hey, I got more than enough energy. I just slip right on by here and I don't have any effect whatsoever. Well, that means you've got to solve this set of equations and actually work through that. So hopefully you have. And if you do work through those equations, you will get the solutions for these coefficients. Again, it's in Iceberg and Resnick's book. He solves the transmission coefficient up here. You see that's got a hyperbolic sine function in it. And he also solves it when the energy is above the barrier down here. What's interesting here is there's a sine function. And sine functions wiggle. So that means that transmission coefficient is going to wiggle. So if you're above the barrier, you won't necessarily just get a flat line now. There will be values in which if you increase the energy, you actually decrease the probability of transmission. And if you decrease the energy, which you would think would decrease the transmission, it'll actually go up. This happens in electromagnetic waves as well for electrical engineers. It's exactly the same process. So I'm going to show you that, and you can play with this at home. So let me take away, this is the single barrier step area that I gave you. And the other one I gave you says is called a small rectangular barrier. And so you've got some controls on there. Now you can't control everything, you have to be a little careful. I had to change the formula in going below the barrier to above the barrier because otherwise I'm going to get a square root of -1. So I pulled that square root and done, just like the book did, the value. So you can't take these cells and make this value here go below 1 or you're going to get square root of -1 in here, it's going to mess it up. Okay, so that's one limitation to what you can do. But otherwise, you can add different amounts. You don't have to add a half. 0.05, you could add 0.02 if you wanted. But then you're going to have some place where it crashes. Most what you can do, though, is change the height and change the width. So right now, it's a very narrow barrier. And what you see is that initially, if you're below the barrier, it's all reflected. But even without getting over the energy, the reflection drops as the energy goes up. It gets closer to U0. It doesn't get U0 until it gets right here. So you still have a negative energy. You get tunneling, transmission, even down here, say in half. For instance, at 50% of the energy of the barrier, you have a 94% probability of going through the barrier. Anyway, that's like going through the wall and popping out on the other side. And you only got 50% of it. And that's because the barrier is so small, you can borrow energy under the uncertainty principle and go through. Now, if I make that barrier bigger, you can see it gets spread out. So now, even when you match the energy of the barrier, you don't get 50% transmission. So it is very sensitive on the width of the barrier. But when you get past the energy of the barrier, you know what happens. Eventually it goes straight up to full transmission, it kind of sets there, and it goes straight down to full zero reflection, it kind of sets there. Now that's not where it's fun. Look what happens now. Now you begin to get these dips and oscillatory things that happen. So you get 100% transmission here, but if you increase the energy even more, so you're even higher above the barrier, transmission goes down. So it's not like just get over a certain threshold, you get 100% transmission. It does not happen. You have wave phenomena. In essence, you're getting interferences back and forth in that barrier. You can cancel out probabilities. Keep going on even higher. These oscillations, you get more oscillations, and the oscillations can have even a bigger effect. I mean, there's a 20% oscillation between here and here in your probability of transmission. You can play around with that. You can play around with. You get even more interesting shape. So I've sent you this. You can play around with it. It simply takes advantage of playing with looking at what happens to a probability distribution as you change the width and the height of a barrier. It's not something that's classical. You can't just ignore the math. You can't just say, oh, well, it's above it, it's 100%. It is not. But it is the way electronic devices work. It is the way that the ammonia atom actually can exist. It's the way that you can build ferroelectrics in order to build memory devices that are extremely long-lived and have the ability to put a huge amount of information. It's the way transistors work. It is a very powerful device for controlling things. And you should know the barrier and know it well. So play with it, because if you don't play with it, you're never going to have a feel for it. All right? All right. Let me talk a little bit about how I got those coefficients, or how the book got their coefficient. So like I said, it is worked out in the book. So I didn't have the world's greatest graphics package, so I didn't draw some pictures that I would normally draw. So let me go back. If you have a point in space, let's go to E and M. Say a box like this. And inside that box is a certain amount of charge. Okay? So charge in a box. Well, if I make the box bigger, I can include more charge. So that's what's called a global law. When you integrate over something, and you talk about it's in this volume, a macroscopic volume. The only thing you can tell me is what happens in the whole volume, but you can't tell me what happens at a particular point in space, like that point. That's useful from an experimentalist point of view, because an experimentalist cannot build a detector of no size. An experimentalist cannot build something that's infinitely fast. So an experimentalist's work, when you compare it to a model or a theory, is always comparing, for instance, to this is what happens in a region, the size of my detector, for instance, or this is what is happening over some amount of time. They can't take a derivative. It's not possible. If they measure a position and then they measure a change in position, it's going to happen over an appreciable time. So it's an average. But mathematics can enable you to do more than that. You can take advantage of things like Stokes' theorem and Gauss's theorem in Calculus 3, and you can convert, as we did back in Physics 2, for those who have need for that, we can convert from a global integral equation to a differential equation. And if you do that here, instead of talking about the Q integrated over some volume, we can take advantage of this and talk about the density at a point. How much charge is at this point? So it's charge divided by volume. And you can take its derivative with respect to time. So if you think about this as an infinitesimally small volume, ds1, ds2, ds3, let's say. Very, very small. All the way to mathematically a point. If the current per volume at that point changes, where did it go? Just disappear? Or does it have to go somewhere? If the amount of charge in an infinitesimal small volume went down, what could you say about the rest of the place?
It also went
Huh?
It also went down.
He says if this charge went here, the charge around here went down.
Oh, never mind. I was thinking like a total measure of the.
I'm sorry, what?
I was thinking a total measure of the entire.
So what do we know about the total charge in the universe?
It's infinite.
Huh?
It's
not infinite.
It's constant.
It's constant. It's conserved. You can neither create nor destroy charge. If you put positive charge somewhere, you had to leave negative charge behind. You cannot just create. So it is impossible for me to build a device that creates positive charge in here and now sucks in New Jersey. I don't know why I'd want to, but the bottom line is I can't do that. You can't just create charge in one place. You can move charge. You can move it from one place to another, but you cannot create it out of nothing. That's true universal. So if the charge in here goes down, the charge somewhere else has to go up. It has to move from one place to the other. That statement is called the continuity equation. And the way it's represented mathematically in 3 dimensions is, it says, hey, look, if it's leaving this thing, it's either got to be going like that, or maybe it's going like this, or maybe it's coming out like this through one of these sides, but it has to go through some side of that box if the amount inside the box went down. So I'm going to have to look. For instance, you can run around the side of the box like this, but then it doesn't leave. So I need to do some sort of a dot product to figure out if it leaves that box. And that's where this equation in the notes comes from. It says if you dot product that thing with this differential here called the divergence, the divergence is a measure of the flow of a vector. And that's the flow of the charge moving, called the current density. If that thing is found to be moving out positive, then what's left behind has to be negative. This thing has to go down. If, on the other hand, this was to go up, then the charge has to be flowing into the box. So the divergence has to be negative. So that's a fundamental relation in electromagnetism. For those of you who've taken E&M before at the junior level, you should know it. If you haven't taken E&M at the junior level, get ready. You're going to see it again. It's just a statement of conservation of charge. In quantum mechanics, we're not talking about charge. But the question is there something like charge that is conserved? And the answer is probability. The total probability of finding the particle somewhere in the space is 100%. So if the probability of finding it in the box goes from 50% to 40%, then the probability outside has to go from 50% to 60%. So the total probability is conserved. So there should be a continuity equation, just like this, that looks like this. My problem is, well, I know how to find charge density. I take charge and divide by volume. How the hell do I find probability density in terms of the wave function? And likewise, this is current density. It's current over area. How do I find that? I mean, what's the formula for that in terms of the wave function? Okay, so, yeah, this equation was told is a statement of conservation. But what are those symbols supposed to be in modern physics? So that's what basically the book, an iceberg and resting, and my notes is attempting to do. So that was the continuity equation there. And in 3 dimensions, if you were to write this in 3 dimensions, it would look like this. The partial of the x component of j with respect to x, the partial of the y component of j with respect to y, and the partial of the z component of j with respect to z. Now that would be a 3-dimensional problem. Let's walk before we can run. Let's say that this thing is only 1-dimensional box, because that's all we're going to do, 1-dimensional pair. If I'm doing a nucleus, I got a 3-dimensional problem. If I'm doing hydrogen atom, I got a 3-dimensional problem. I got a 1-dimensional barrier. So I just basically eliminated those 2. There's no need to have the x on it because it's 1 dimension. The only value you can get is plus or minus. You don't have I hats anymore. So I just dropped that down here. And something else, you may say, well, what about full derivatives? Well, you can't do full derivatives because you still got time. So there are still 2 things that this thing can depend upon, time and space. So it's a spatial derivative with respect to x plus a derivative with respect to time. Question is, identify what the heck this is in terms of the wave number in the Schrodinger equation. Determine what the heck this thing, probability current density, in terms of that. That's my problem. The first one was pretty easy. I know what probability density is. It's a distribution function, and the distribution function is the wave function squared. So I know this one. It's psi star psi. That's easy. And I can find that with the Schrodinger equation. What I don't know, or didn't know, is what J is. So to find J, what I have to do is I have to say, hey, I gotta obey whatever the main fundamental equation of the problem is. Well, in E&M, the fundamental equation are Maxwell's equations. In mechanics, the fundamental equation is Newton's law. What's the fundamental equation in modern physics that we've been using? Huh? Schrodinger. So whatever this thing is, I should use the Schrodinger equation to find it. So what we did is, since I want to take a derivative of this thing, if I look at that, I'd say, hey, look, if I try to take derivative of this, that's going to be the derivative with respect to time of psi star psi. And that's going to be psi star d psi dt. And then I'm going to have a psi d psi star dt. And if I look at that a little bit, it gives me the hint. I need to find d psi dt, but that's in the Schrodinger equation. And the Schrodinger equation is the fundamental equation to use. Now, it's not, the Schrodinger equation isn't quite d psi dt. It's got this ugly IH bar out in front. But that's just a number, a constant. So I can divide both sides by the constant. And likewise, I'm going to have to find what the derivative of the complex of the wave function is. Well, heck, I'll just take the complex of both sides. If I do that, that'll change that to psi star. And it'll still be the Schrodinger equation. It'll just be the complex conjugate of the Schrodinger equation. So, take the Schrodinger equation, take its complex conjugate, divide by minus IH bar here. You can divide by IH bar there. And you got d psi dt, you got d psi star dt. That's almost what you need, except you need to multiply by psi, that psi star, that equation, and you're going to need to multiply the bottom equation by psi. And then you're going to need to add them together. And so that's what I did. And hopefully you went through those steps. So there was the IH, and I multiplied by psi star. There was the minus IH, I multiplied by psi, that's the bottom. I said, hey, that's almost what I need. If I leave the minus here, I'll tell you what, if I subtract that, that'd be psi star d psi dt plus psi d psi dt. So I subtract it, and I pull the IH bar out front. Well, that right there is this, where I've divided the IH. That's why I killed one of the H bars, and that's how the I got in the bottom. And then this, that's just rho. So I found d rho dt. I found that part. And what's that equal to? Well, let's go back. dj dt plus d rho dt is 0. D rho dt, therefore must be minus d, I'm sorry, that's an x, must be minus dj dx. Hey, that must be minus dj dx. Now my problem is I still can't identify j because I don't have a derivative here. But it's almost there. So I sit here and I look at it for a minute and I say, hey, look, there's a second derivative. And I'd like to have a first derivative. If I took a first derivative and I took another derivative, I'd get a second derivative. So what I need here in j must have first derivatives. So when I take a derivative, I get second derivatives, like I've got over here on the side. So I said, well, hey, tell you what, why don't you try this? If you put psi star d psi dx, and you subtract psi d psi star dx, that's going to give me my second derivative, like I got there. And when I take the derivative over here, that's going to get me my second derivative of psi star. But I'm going to need some other terms. And I'm going to have to see if those terms cancel out. So I just took the derivative with the power rule, product rule. So I get the second term where you let this guy fly and go through there. Then you get the derivative of the first term times the second. That's that one. So these two are the derivative of this, with the product rule from calculus 1. And then I do the same thing on the second term. So I get a derivative of psi d psi star dx. And it doesn't matter which way you write them. You can write them in either order because they're independent. I can either write this as d psi dx, d psi star dx, or you can flip them. I chose to flip them, so they look just like that guy. And then minus, you let it go by this one and take second derivative here. Well, this term and this term cancel. So that can be replaced there. Nothing fancy, just calculus 1. Hopefully you master calculus 1 of the product here. So if I substitute what I found, on the left-hand side I have dj dx, and on the right-hand side I have d dx of this bracketed thing. But that bracketed thing has to be j by comparing the two equations. So I didn't know what the current probability density was. I never heard of a probability density, but that's it. And it behaves just like a current. It's the flow of probability across the box. Now, this probability current density enables me to find transition and reflection coefficients. A reflection coefficient is the probability density that's reflected divided by the probability that entered. In the same way that a reflection coefficient is the current density reflected divided by the current density that came in. So because I found the J's, and because I know this is true in E and M as well, this is the definition of the reflection coefficient. And I have a formula now for calculating J's. So what I need to do now is I need to take this formula and I need to take your problem and find what your incoming wave is, say the plane wave, and find what your reflected wave was from your solution. And I need to calculate their J's, and I need to divide their J's, and that gets me the reflection coefficient. Or if I want to do the transmission coefficient, I can put in the wave that went through the barrier in here, calculate its J, and divide by the J that came in for the instant wave, and I get your transmission. You add those two, they got to always equal 1. So I don't know about you, but I don't like to do all this J calculation, so I'm going to calculate one of them, preferably whichever is the easiest. And then I'm going to do 1 minus that to get the other one. Because I can do 1 minus 5, 1 minus 0.5, that's 0.5. 1 minus 0.3, that's 0.6. I do that pretty quick. I'm pretty good at that. Doing complex conjugates, derivatives, that's a little bit more tricky. So I'd like to find some easy things. Something else to note. If psi is real, then psi star is equal to psi. Now it turns out psi itself can't be real, but the time-dependent part is the same, and its conjugate is the same. It doesn't have a derivative with respect to position. So whether you call this time or only the spatial part, you get the same answer. The time to part does not matter because there's no derivatives of t anymore. Remember that this thing is actually the spatial part times e to the minus I omega t. But since the time isn't in here, it's going to come out, it's going to touch its e to the I omega t, and it's going to cancel out. So you might as well just ignore time. So if the spatial part, in essence, is real, then when you take its complex conjugate, you get the same function back. That's important, because it says that if this thing is a real thing, like an exponential decay, then you can just ignore those. And you get psi d psi dx minus psi d psi dx, and what's that? 0. And there is no current density for that thing. You cannot represent a moving object with a real wave function, a real spatial wave function. It's impossible. So if you want to represent a ball moving through, an electron moving through, whatever, it's got to have a complex spatial part. Cannot be represented otherwise. Now, in our barrier where we were below the barrier, so we had this thing like here. This side, the transmitted side, our wave function looks something like this. Is that a real or imaginary function here?
That's a real function.
Huh?
That's a real function.
It's a real function. So therefore, what will be the current density of this transmitted part? 0. So when you put 0 divided by something, you get 0. So t is 0, so what's r? 1. You can calculate all the k's and do 1 and prove that on r, but that was an easy calculation, so that's my choice. All right? And that means I can go back over again. Those are my little... That's why you get 100% reflection here and no transmission. Until this thing quits being a real function, okay? Till this thing quits being a real function, which will not occur until this thing gets up here, you're never going to get transmission. Because you got a real function, and that means you got 0 current density, or 0 probability density. Okay? So as long as you're down here, and as long as this thing, why does this thing have to be infinite? Because if it comes back down, then this is the region of transmission. And in that region here, it's not this function. That's the function in there. In this region, it looks something like and then we get rid of this one because it can't be going reflected, so it's that. But that's complex. That's not real anymore. So now you can have transmission. So that's a nice trick to be on the lookout. If you have a real function, the current density for that, the probability density for that is 0 every time. No need to do a lot of math. You should know that off your head. It's a great question to ask on, for instance, a field of study examination. It's a great question to ask on an FE. You know, an FE exam, you got, for instance, 3 hours, you got 180 minutes, you got 120 questions of engineering to solve. You haven't got time to be doing long calculations. If you don't know the tricks of trade, you ain't going to get licensed. It's just that simple. The same thing in the field of study exam. We require every physics major here to pass the National Field of Study major exam. All right, you want to take a GRE and get to good grad school? Same thing. It's a quick base test. They're not going to be able to ask you anything that's got extensive name, but you should know the basic things that you need to know. This is a good one to know. All right, so one of the things they can ask you about barrier is that if you could tell that thing's a real thing, then this J is going to be 0. All right. So what I did with that, the other thing that you should really know is you should know something about what the result should look like for a plane wave. Why? Because plane waves are the simplest type of shape, whether it's electromagnetism, or you're far away from the transmitter of the radio station, or you're talking about a plane wave barrier like we have here. Spherical barriers are 3-dimensional, so it's not even a 1-dimensional problem. It's already going to make it harder. All right? Plane waves are the easiest. You should know the answer to the plane wave. So I worked the plane wave for you. I want to look at the solution to that. The incoming wave was AE to the I K1 X minus omega 1t. That was the spatial part, and that was the time part. And again, like I said, you can leave the time part out because it isn't going to make any difference. You see the plus and minus come, they end up wiping each other out. They should have wiped each other out if I'd have done it right. Somehow, I have not done this correctly. I'm not sure which one. One of these should be a minus. Okay, that should have been a plus. This should have been a minus. And that was that should have been a plus. This should have been a minus. So that's my fault. There is an error there. When you conjugate the time part, one of those should have been turned to a plus, and one of them stayed a minus. So this was the non-conjugate. The conjugate should be moving, have a plus there. And so that would have canceled those out. And I canceled them out, but I obviously lost a sign here. So what do you get? You get H bar K. What's H bar K?
H over 2 pi.
Huh?
H over 2 pi.
It's H over 2 pi. No, K is 2 pi over lambda.
Let's say that's Roy wavelength, right?
Huh? What did De Broglie say the H bar K is?
Lambda, well,
That's fine. Let's if you don't know it off your head, you should. Let's deal with your lambda. What's K?
it's 2 pi over lambda.
Okay, I agree with that. What's H bar?
It's H over 2 pi.
I agree with that. Okay. So 2 pi's cancel. What's H over lambda?
HF.
Huh?
HF.
No, not HF.
It's momentum.
It's linear momentum. So this is P. So the top here, that's P. So what's P divided by N? Physics 1.
Velocity.
Huh?
Velocity.
Velocity. So that's V. So for a plane wave, a general statement is this. That current probability is the velocity of the wave times the square of that A, that amplitude, if you want to think of it that way. if you have a bigger A, think of it as a bigger wave, then in a given amount of time, you can move more stuff. On the other hand, you can have a small wave, let's say a water wave, but to have the wave move a lot faster so you get hit by a bunch of waves. So instead of getting hit by one wave, you get hit by 37 waves in the same amount of time. Then you can still move the same amount of stuff. All right? It's kind of like thinking I can put one deposit of $100 in the bank, or I can put 10 deposits of $10 in the bank. And I will move the same amount of money either way. So it depends on two things. How big it is, and how fast, meaning therefore how many of them are coming in and putting it in. The other way to think about it is it just cuts down that time. Remember, current is dq dt. This is probability per time. Cut down the time for the same probability, you get a faster probability transfer. If this velocity was going in the negative x direction, there'd be a minus sign in front of it, because it's a velocity. If you work through the reflected wave, you do get the minus sign. Remember, that is a kind of half. That's just like a h bar k. So that's the magnitude. That's the speed, if you would. There's the minus sign. So it's velocity times how big it is. If b is bigger, you get more current density. If it's moving faster, you can get more current density. Go back and take a look. If you played with the continuity equation, you'll see the same sort of thing comes out in electromagnetism. You only have X number of hours in the day to study. You guys don't put in enough. I can tell you that. But besides that fact, when you study one course, if you're going to be good at it, you have to also be getting double credit by learning the other course at the same time. If you're not, somebody who is getting twice as much credit for the same amount of time. Seeing connections between courses is a big thing. If you don't put in enough time, you don't do it. And that means you don't just fall behind them. They got, you put in 1 hour credit, they put in 2, but their 2 hours got them 2 for this course and 2 for the other. So they got 4, you got 1. They're 4 times further along than you are. And you do that over time, and they will leave you in the dust. All right? You got to see the connections. If not now, when? When you leave, you're going to be busy working. You're going to have a full-time work, and then at night you're going to have to stay competent in your field. You got more time now than you'll ever have. So go back and figure out how to connect stuff. It's the key to being really strong. It's the key to being able to see stuff. There's a lot of good physics and good electrical engineering in this chapter. It will help you in other courses and save you a lot of time. You can do the same thing for the transmitted wave. No necessary. I wouldn't waste my time to do those derivatives. I know the answer. It's P over M times C squared. That's K. I know what that is. That M. Know what that is. If that K is imaginary, then so is that an imaginary current. Okay? So I take that, put it in here, and if I do that for the same region, notice the K's cancel. Why the K's cancel? Because the first barrier, the reflected wave's in the same region, moving at the same speed as the wave that comes in. If they didn't, let's say that the reflected wave moved real slow, and you had some barrier like this, like a water wave. And so here comes this wave, it bangs in here, but then it slows down on the wave back. Well, here's another wave coming in, and another wave, and another. You get all these waves coming in, hitting the barrier, but they're all staying here. Then the water would eventually go up, 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 and up. I mean, think if it went zero and all the water stopped at Galveston Bay, right at the edge of the seawall. So you sent in 1 foot waves, but when they hit, they didn't go back. Then you'd have a foot on top of a foot on top of a foot on top of a foot. Pretty soon you have a 6,000 foot wave. Okay? That doesn't happen. They come in at 1 meter per second, they go back at 1 meter per second. That's what happens. Okay? You can sit down and figure out why that is in terms of energy sometime. Okay? Throw a ball against the wall, why does it bounce like that? Throw a ray of light, why is the law of reflection the way it is? You should be thinking about things like this. So this wave comes in, hits, so that K cancels that. The minus sign's inside the absolute value. So you get this, and that's what I wrote previously in the notes. So the ratio of those coefficients, B and A, determines the reflecting coefficient. Now, we know when you go through and work through that whole thing, you get 100% reflection in the case where the alpha is involved, so you can then figure out what B has to be. Okay? Tunneling gets harder because there's more things to calculate. But the calculation and the idea of current density is the same. All right? It's just a matter of you calculating. If you have, for instance, a barrier that goes like this, then this K here for transmission will not be the same K. It does not move at the same speed here. So you'll have to account for the Ks. So the transmission is usually not C over A. It has more to it. So let's look at that. There's C squared, there's A squared, but what's over it? There's velocities. If they're in the same region, they cancel. In this case, they were because his barrier was such that it went back down. But if the barrier had been higher, then this V here would not be the same as that V, and they would not cancel. Don't leave that term out. It's common when you get people on GREs and FE exams and field of study exams because they just write C squared over A squared. That's not true. That's a special case. It's always the square of the coefficient times the velocity in calculating the current density of a plane wave. Only if it's in the same region with the same potential does it cancel. Nobody said they couldn't give you something that came like this. They certainly can, and they do. And they also give you a lot of times where it's like this. Write in with the B's and cancel the B's if you can. But don't forget the B's are there for the transmission. Reflected, not a problem. In the reflected, here's the wave, there's the wave. They're all in the same region. They have the same B's. They will always cancel. So you could say, where he writes the R, see if I can find his R coefficient. I'm sure I can. You could say when he has an R coefficients, see if I can find an R. Yeah. There's B1 and B1 as well. And the B1s cancel. The B1s will always cancel because they're always going to be in the same region. But if you want, you could always write it like this, and then you wouldn't get messed up with the transmission coefficient. It's just that these are always going to be the same, and they'll always cancel. And the others are not always the same. They don't. All right, we've left that. Start just a little bit because you've got a lot of reading that you haven't already started on harmonic oscillator. Step potentials are easy. The math is easy. There's some algebra in it, but there's nothing really very advanced. Constant coefficient differential equations. You can memorize the solution, and you can write them down off your head. That's what we like. In general, no real barrier behaves that way. A real barrier probably behaves something like this. The particles in here, something like with this energy trapped in this barrier. Where did I get this? Well, this thing could be like a Coulomb potential and go as 1 over R. Now there can be other potentials. If it's three-dimensional, you'll have to add the fact that angular momentum has to be conserved for a central force. When you do that, you get a term that's the rotational energy of the problem. And it's because you usually want to convert it to a one-dimensional problem, they move that term over and they call it the centrifugal barrier. This is kind of like being in one of those rotated reference frames where you think you're not rotating, you're setting still, but because you are really rotating, you got to add extra fictitious forces. Now they become fictitious potentials. So how do you work a problem like that? Well, that's a real world problem. Why don't we just cut it up into a bunch of little bitty barriers? We'll calculate the probability to get through that barrier. Then we'll calculate the probability to get through this barrier. Then we'll calculate the probability to get through this barrier. The probability to get through that barrier. That barrier. That barrier. That barrier. So on and so forth. So we can apply. Now, I wouldn't want to do that by hand, but a spreadsheet's no problem. Okay? And you can get a very accurate measurement, actually, for ground states for radioactive decay probabilities for alpha particles. In fact, we used to require that at cadets at West Point. So you can get if you don't account for angular momentum to excited states, you do not get accurate measurements for some things because you're not using the right potential for the barrier. But that's what people do. They take the barrier problem and try to do this. You can't do that with a harmonic oscillator. The reason is that's its potential. Find me the region in which it's going to be flat. There is no such place. So because there is no such place, you've got to solve the whole problem in one step. And that means you've got to solve the differential equation in one step. And that's difficult. Okay? Not impossible, and it requires certain skills that you should know, which is why we do it. The other thing to note is we don't write the harmonic oscillator potential like that. Why not? We did it all through Physics 1. Well, in Physics 1, we dealt with things like this. You know, you had some sort of thing here, and then you had a spring, maybe, and then you had some mass. And if I wanted to find the spring constant, I could remove the mass, hook up, apply a force of a known amount, and see how far I could stretch that spring. How are you going to do that inside an atom? You can't get inside the atom to actually measure the spring constant. It's some collection of forces. Okay? So we try to rewrite it in terms of things we can measure. The frequency of the stuff it emits and the mass of the particle. All right. See you guys next time.
See you later.